Okay, so uh, let me start the recording. Oh, recording has started. Thanks. Right. Okay, so we are discussing about this Bayesian learning, and in the last class, we discussed different kinds of approaches. Basically, it's a probabilistic approach, and even different other intuitive approaches. What we have learned for classification or regulation, we can see that uh, some of them have Bayesian interpretations. Like I just discussed about uh, these two things. I mean, one is as you see that in the even the version space, that means concept learning, that can be also considered with respect to the under the Bayesian framework, because what we are computing here, because we are assuming there is no error in the training data, so you can define the likelihood function in the way it has been given. As you can see that if the data sets, so when you are considering an hypothesis which is consistent hypothesis, then definitely the likelihood of that data would be 1, probability would be 1, and the prior would be would be taken with any uniform distributions. That is the kind of assumption. So any hypothesis has equal probability for getting selected, and then the marginal probability of data would be uh, this. So that means if I consider the likelihood of each hypothesis for each hypothesis for the data, then it is basically the weighted. Basically, this is a joint probability of data and hypothesis and over hypothesis space, and that is a marginal probability of data. So that can be expressed in this form. And finally, if I consider the posterior probability, that means given a data, what is the probability of choosing that hypothesis? So if it is in the version space, then it is 1 by the size of the version space. That means any hypothesis in the version space can be selected. With they have all equal weightage. Whether and also the hypothesis which does not belong to a version space, that is not going to be. So their posterior probability would be 0, which means no, they are not going to be selected. Similarly, when we consider the least mean squared error estimates, and we can see that this is a kind of maximum likelihood based approach hypothesis. Though it is not on Bayesian inference, but it can be explained under the same framework of probabilistic interpretations, because in this case, you may consider that your hypothesis given an input data will predict the output. So the true output is yi, and that means that's the observed. I mean, that is the true output. So when you are estimating the corresponding function, there is an approximations involved, and that approximations you can consider that these observations may be noisy also. So you can consider there is a deviation or there is an error EI terms, and if I consider the EI is following a Gaussian distribution, so probability of that value of error, it's a Gaussian distributions with mean 0 and standard deviation sigma, then we have the probability of the corresponding data given the hypothesis can be expressed in this way. So it's a joint probability distributions over all errors, and they are they are occurring as an independent variable, identical independent distributions they are having. And so this is the joint probability of all error terms for individual observations in terms of Gaussian interpretations if they follow the normal distribution. And your objective of the maximum likelihood estimate is to get that hypothesis which will maximize this joint probability. of I'm saying joint because no, each individual observation is given this term. Actually, we are going to maximize this probability, that the likelihood of the data given hypothesis. So maximization means we can see that actually that problem is equivalent to minimization of the squared error terms, what has been shown in the color red, which is equivalent to this particular problem. That means mean square. It is basically mean squared error, so it should be divided by 1 by n in that sense. Then it is mean squared error. Otherwise, it is sum of squared error that you are minimizing. Okay, so that can be straight away you can show that relationships, because if I take the log of likelihood values, still the problem remains the same for maximizations, because it is equivalent the hypothesis which will maximize the likelihood, the same hypothesis will also maximize the log likelihood. So if I take the log, the term becomes like this, and you see that the variability is here. In this part is a variability. So maximization of this expression means minimization of this expression, and which is equivalent to minimization of this. So this is how your mean squared error estimate or least mean squared error estimate is equivalent to some kind of I mean the approach is under the same framework of maximum likelihood based approach for selecting a hypothesis or a target function. Now another kind of criteria could be there for choosing a hypothesis, is that if I consider the description length, total description length, that means hypothesis which is predicting the data. Now, if I consider the length of the hypothesis and also the length of the or the amount of the deviations, if I store them, I can store actually the whole observation itself. So either I can observe the whole observations, like you have a training data. Let me explain that. Say, in this case, I will come to that. So in this case, you have this the Bayesian inference. That means maximum a priori posteriori probability. That hypothesis which is maximizing this posterior probability, that is selected in this fashion. So we can consider that, which means that you are also maximizing the log of posterior probabilities. So it is proportional. You see that it is not exactly posterior probabilities, it is proportional value, because the denominator term of the marginal probability is not used here, because it is same for a given data. So which means that the same hypothesis will minimize this expression. That means if I negate those terms, and as you can see, these are all entropy terms in terms of they are the description length of optimal encoding for a hypothesis. So in the hypothesis space, which is I mean, this is basically optimum length of the hypothesis, and this is the length of the information data given the hypothesis. So what is the amount of redundancy is there or information? So this description length should be minimum given that hypothesis, and or it has an information theoretic interpretation. So because you know that optimal encoding length of a message of probability p is minus log p. So in this way we can consider that. So these are several other as I say, that other kind of criteria which may not be directly related or directly inferred from Bayesian under Bayesian framework, but we can put them under the similar probabilistic framework, which could be Bayesian or which could be maximum likelihood based inference also. Now, this also gives you another interesting insight, that because you have the options of choosing an hypothesis, as you see, and there is a kind of strength of choosing that hypothesis. We are also defining a measure. And what is that strength, or what is that weight? That weight is the posterior probability. That means given a data, you can choose an hypothesis, and then the weight could be the posterior probability of that hypothesis given that data. Okay, so if I consider the whole space of hypothesis, that means if I consider this, that posterior probability of hypothesis and given data, it is also, you can consider it is also an weight of an hypothesis for its considerations. Suppose I am considering every hypothesis in the hypothesis space, and what I am trying to design, I am trying to design an ensemble classifier. Okay, the aggregation of the decision. So every hypothesis is giving me, some value of the target functions, right? So what we may also take a decision. I may consider each and every hypothesis decision, but they should be weighted by this factor. Okay, and what is the sum of weight? What should be the sum of weight? That means if I consider all hypotheses, that is the sum of weights, and that should be equal to, what should be this value? Sum of weight? Anyone?
The probability of H.
Can you repeat, please?
The probability of H.
It will be of
Probability of H.
probability of. Now, actually, see which H, because I'm H itself is an argument. So I'm taking each and every H, and then I'm taking its posterior and then summing them. So, so which H you are talking then in this case?
Sir, complete hypothesis space.
Is a complete hypothesis space. Each and every H you are considering, and then I'm summing its posteriors for each and every hypothesis. In fact, I told you that becomes also weight. So it's a probability distribution. So it is basically probability of choosing this hypothesis given this data, and there are so many alternatives. So ultimately, what should be the sum of these probabilities? They are all exclusive probabilities, isn't it? So what should be the sum of this
Probability of
probability?
Gaussian space.
So it will be 1.
It will be 1, sir.
It will be 1. Yes. Is it clear? Now, this is something we should know. Then that's why this denominator term is important. If you don't use denominator, then this equality does not hold. Like if I simply use a numerator which is proportional, I need to take this call, please. Someone microphone is on. Please mute it. So this is what we are considering. Okay. Now what I am saying that this is the weight of a particular hypothesis. So this is the weight of a particular hypothesis. That means if I consider a unknown input x for any input x, so what should be the output of that function? I mean, if I choose a hypothesis h, output would be hx. Right? Let us consider these are all numerical values. Okay. So output is hx. If your input is x, then say output is hx. If I and this is what this is your hypothesis. You are trying to mimic the target function. So this you are considering that is representing the target function. Anyway, so but if I consider each and every hypothesis, then what I will do, I will weight this output with the weight of that hypothesis for the for being for being considered with this training data set. And then I will take the sum over them. So that is what is your ensemble technique. Is it clear? Right? And then this decision, we call it an optimal, decision. And if it is as a classification decision, for example, so now you consider what kind of weights, etc. will be doing. So if it is a categorical data, there are issues. But let us consider, say, you are doing this kind of numerical operations, and then we consider that is your optimal classifier. So what we can consider here also, say, I will take this decision. So I will give an example, then these things will be much more clearer with respect to classifications. Right.
So can we prove this theorem by Bayes theorem?
Pardon?
So can we prove that fact by Bayes theorem also?
Yeah,
That,
it would be coming. It
summation
will be
equal
optimality
to
criteria will be coming from Bayes theorem itself. Yes. So we can say that you can learn a target function of a classifier, and a target function is this. So I'm just explaining once again the same thing. I'm just going through my slide set. And as you can see that you have a set of possible class levels, V1, V2 to Vk. And let us assume that your class levels could be some numerical value, or for binary cases, it is simple 0 and 1. And your hypothesis space H with your Hx goes to V. I mean, that is understood. And as I mentioned that if I choose just maximum a priori, probability based, maximum a posteriori probability based hypothesis or MAP approach, then the criteria would be this. That means you choose that hypothesis which has the maximum posterior probability. That is the maximum weight, if I say. It could be multiple hypotheses also in some cases. Like when there are conflicts, that means multiple hypotheses with the same posterior probability, and they are maximum also, or they are maximal in that sense, hypothesis. So you can choose any one of them. But say this is a criteria, and as we say that in decision making becomes optimal if we weight them by their posterior. When we say that we choose that particular level. So in this case, as you can see that instead of Hx, so this is the context of classification. In my previous case, I have considered Hx as the simple way of giving the levels. But here, we have this probabilistic argument. That means probability of a level given H. Now, when it is a very crisp, that means only one level, for every input there exists only one level. That means the probability of that level is 1 and others are 0 in a usual scenario. But no, you can have probabilistic inference here also in this target functions also. So this is what. So you have the probability in your hypothesis, actually you are doing it. So you get a probability of levels. So now you consider this, the weighted values of these probabilities, right? Weighted values of this probability of this level. And wherever it is maximum, which level is giving this maximum probability assignment, probability of given that hypothesis in the hypothesis space itself. So you consider to take that level. So this is the difference here. I have an example which I can give you. Say this is an example. Note this example, and this example actually demonstrates that decision making process under these optimal conditions with the usual way we choose also the kind of making decisions of a particular level. So what we see that your set V, you can just note these values. that your level set of levels, there are two classes. One is positive and negative, and your hypothesis space, you have three hypotheses. So let us consider only you have three hypotheses, and given a data, now you will have its posterior in this way. So if I sum these posteriors, it would be equal to 1. So if I consider this is the only hypothesis which are there in your hypothesis space, so naturally the sum of all these posteriors should be equal to 1. So now this is your posterior distributions that you have computed, for example. So naturally, when we consider the H map, when you consider H map, you have you can select H1. Now H1 has a specific level. So for example, for an instance, you have these are the kind of output given X. So output is either positive for a hypothesis or a negative. So we are not having a probabilistic interpretations while denoting this output, but no, we can make it probabilistic interpretations by saying that probability of level positive given given H1 for the input X is 1, or probability of level negative given H1 for this input X is 0. So in this way, you can have the probabilistic interpretation. So yeah.
So can we say that H1, H2, H3 are consistent hypotheses?
H1?
H1, H2 and H3 are consistent hypotheses?
No, it's not the question of consistent. It's just their hypothesis, and there are probabilities. They may not be consistent also.
So they are not present in the version space?
See, it is not a question of version space. Yes, it is not version space. It is the whole hypothesis space. When I talked about in the previous case also optimal classifier, we are not restricted to only version space. Now, if you are considering the concept learning, naturally the posteriors are 0. So those hypotheses which are not included in a version space will not be considered. Yes. Because the weight itself is 0 there. But we are considering the whole hypothesis space. Okay?
Yes.
So in this case, as you see that if I consider HMAP approach or map approach, then we are selecting H1, and naturally the level of this instance is positive, right? This is the Bayesian inference on this particular set. But what is the decision of optimal classifier? There we can see that what is the probability of being positive given H1. So first we will be considering what is the probability of level positive for the optimal classifier. So for each component like this, there are two components in this. See, one thing you are computing what is the probability of being level positive considering every hypothesis, which means they are weighted by their corresponding posteriors. Okay, these are the posteriors, and these are the probabilities. So naturally, this probability is equal to 1. Okay, this probability is equal to 1 given this fact. But what about this probability? This probability is equal to 0, and this probability is equal to 0. Is it clear? Similarly, for the negative level, you do the same computation. So here this probability is 0, but this probability is 1, and this probability is 1. So if I compute them in the same way as I mentioned, you can see that what you are choosing, you are finding that actually the value of this optimal classifier given X is becoming maximum for the negative level. You can see there are two values, 0.4 and 0.6. So argmax means the level which will maximizing it, and that is negative level. So you have to choose argmax, not the max. Okay. Right. So naturally, then the level becomes negative. So it is not that the map approach will always give an optimal decision. That you should understand. But it's an exhaustive enumeration. That is the problem. So there are some kind of pragmatic approach which takes care of this factor, which shows, as I mentioned, which shows that your decision making could be made optimal if you consider all possible hypotheses weighted by their posteriors. But as you see, that is not very practical. So can there be any other kind of inference mechanism which will try to get an optimal, near optimal behavior? So one of these algorithm is Gibbs algorithm. So what it does, that it considers a probabilistic way of choosing any hypothesis, and this probability is proportional to the posterior. That's what. So it chooses a hypothesis H randomly for an instance X with posterior distributions, and then apply H on that instance. And then, so we say optimal actually with respect to a given set of observations. So if I consider a single instance, no, it may not be, optimality may not be established. But if I consider a large, on the large occurrences, large number of instances, and on the whole, what is the error between your inference and the true values? If I consider that scenario, then the optimal performance would be there with respect to optimal classifier. And Gibbs algorithm also may give you a better result than the map approach, and at least it has certain bound, theoretical bound, which is not in the scope of my discussions, and neither I am also very much thorough with that analysis. So, but no, I'm just providing you from the algorithmic point of view that these are interesting things. You may have a detailed study and to find out the theoretical inference, theoretical analysis behind it. So it says that it's expected error at most twice of the optimal error when the prior has uniform distributions. So that is the result where Gibbs algorithm can be there. So just to summarize, yeah.
So what was the drawback of the Bayesian method, like map method?
What is the?
What was the drawback, like where it went wrong?
So you see that the map approach also should be a near optimal, but the drawback is that first thing, the map hypothesis also may not be the true target function. Okay, so what we are trying to do, we are trying to get a hypothesis, get some this inference mechanism so that your target functions gets realized. Now your target functions may not be realizable with the kind of hypothesis structure, formulations, etc. So we are using probabilistic interpretations in this case, as you see. So given a single hypothesis, target functions may not be realizable. So it may be the ensemble of hypothesis decisions in different conditions that may be suitable. So target function is complicated. Okay. So the optimal classifier is trying to provide you that kind of mechanism where you consider each and every hypothesis contributions in your inference, and it will give you your decision making, optimal decision in the sense that you will commit less number of errors, or your deviations from true value would be the minimum over a large number of instances, once again, statistically, basically. So this is the difference, right? So you try to understand from that angle. So map hypothesis is a particular hypothesis which may satisfy for a large cases, but which may fail also for a number of cases. So what is Bayesian classification? So that's a summary in my discussion. As you see that in this case, input is a training set of tuples and their associated class levels. We have discussed with respect to, because it's a probabilistic inference. So it is sometimes it is easier to discuss with respect to the dimensional space and their distributions, etc. So anyway, so input is a feature vector, as you can see that, and if there be m classes, so you are trying to derive the maximum posteriori probability, and the class which gives you the maximum posterior probability, for which the probability posterior is maximum, we assign that class. And this posterior probability is computed in this fashion. And also we have discussed that no, this marginal probability Px is constant given the value given a particular instance itself. So this is actually proportional to the numerator part only, and it is enough to compare the numerators when you take a decision. But once again, as I mentioned, that limitation is that you do not know how sound is your decision, right? For that computation of posterior, I mean, it is preferable. It should be there. Now, I will give you once again some other kinds of classifiers, which I will discuss later on also. One of the kind of classifier is a discriminant function-based classifier. Again, a discriminant function-based classifier also has a Bayesian inferencing interpretations. So that let us review that part also. So what is a discriminant functions? So let us first understand what is a discriminant function. Say we consider a set of discriminant functions, and suppose they are denoted by this functional form, so GIX for the ith discriminant function. So rule is that for every class you have a discriminant functions. You have a function. For every class you have a function. So GIX, say for example, for class Ci. Now you assign the class Ci to a sample X if it is if its discriminant value is maximum over all other classes. So that is what is expressed by this rule. So then we call this kind of classification or classifier is a discriminant function-based classifier, functions-based classifier. And these functions, that's why the name discriminant term came, because they are discriminating a particular class using these functions. Now, in the probabilistic or in the Bayesian term, as you can see that the posterior probability, that expression itself in the functional form, that becomes a discriminant function. Okay. Or you can consider also that if we simply ignore the probability of X, that term in the posterior probability, that means the denominator term, then you can have also discriminant functions in this form. That means only with the numerator of the posterior probabilities term, as we have discussed. So likelihood multiplied by the prior, that's the discriminant function, right? Now, if we consider only two classes, a single function will do. You do not require two distinct functions, because no, you can express a function as a difference of these two, and since you are comparing them, so the positive, if the value is positive, then the G1x is greater, which means you assign class C1. If the value is negative, then G2x is greater, which means you assign class C2. And if the value is 0, it's a fuzzy case. You do whatever you like for the sake of completeness. Anyway, so these are the things. So when we are, I mean, this is a discriminant function-based interpretations. We'll discuss about once again the discriminant functions later on, and the functions when it can be expressed. Also, it can be derived from the probabilistic approaches. Then we have the Bayesian inference, the same, that they are equivalent to the Bayesian inference mechanism. So let us consider also that what are the challenges in computations of this posterior probability. So we have not discussed much about that. So as you can see that when you are computing the posterior probability, mostly you are needed to compute the product of likelihood of a vector for a class, likelihood of a class likelihood, and the product of, and also the prior of the class prior. So these are the two terms you need to evaluate. So which means that you should have a model for these probability distributions. You should have a model for class distributions, and sometimes empirically you can observe them. We also discussed there are different ways by which you can model them. there are parametric methods, non-parametric methods. Very soon we'll be discussing them also. So this is one thing, that how do you model these probability distributions? And this particularly is more involved if this feature vector or X is multidimensional. No, that is also another challenge. So this is what. So how to get the prior knowledge of probabilities of classes, and in particular the considering, if I consider the likelihood functions, then how do you express, how do you get a probability distribution in a multidimensional feature space, which is more involved modeling than modeling a single dimensional feature. So that is what it is. And when we are considering multidimensional feature space, means there are, each dimension is represented by certain attribute or certain variable or certain random variable, and you see that it is basically the Cartesian product of all these spaces. So this modeling can be simplified. Particularly, I'm talking about the handling the multidimensional feature space and modeling the class likelihood into that space. If we use a simplified form of Bayesian classifier, which we will be considering naive Bayes classifier. So it works on a simplified assumption that in this case, the attributes are conditionally independent. That means if I consider a class, given a class, say all attributes within that class, their occurrence, they are all independent random variables, right? In every class, they are independent random variables. So that is what is a conditional independence. So they are not, so given that class, then attributes are independent variables. So in that case, what you can do, you can consider that this class likelihood of the multidimensional feature vector X can be expressed simply as a product of likelihoods for that class for individual attributes. So this is what is a simplification, and that makes your computation much more simpler, because the estimation of class likelihoods of a single attribute is much more simpler, right? You are simply observing the occurrence of that attribute within a class, and then you can estimate these probabilities better there of its different. Attribute here means a variable, right? Of different values of those attributes or variables. So it significantly reduces the computational cost, and as you see, requires only the class distributions. So it is very convenient to estimate this form, like when you have a single random variable given the class distributions. So just sorry, let me take this call. Okay, so we are discussing about this, naive Bayes classifier and the simplifications that can be made in the computation of the likelihood of the multidimensional feature vector given a class. And in that case, it is equivalent to estimation of all unidimensional attributes in the class, likelihood of unidimensional variables, which are used for defining the feature, or every feature dimensions you do it. So for a categorical or discrete variable also you can compute, right? Numerically you can estimate that fraction of times the value occurred in a class. And for a continuous variable, you have to use certain distribution model. You can use certain parametric modeling of Gaussian distributions. Otherwise, that you can have this distribution, cumulative distributions, and you can do some estimations along intervals, empirical way. But normally, when you have continuous variables, you do it with a parametric modeling. Right. So likelihood estimate, as I was mentioning, that it is equivalent to estimation of likelihood of individual features or individual attributes, and then you simply get the multiplications. Yeah, so I think this is the same, whatever I was discussing in the previous slide, it is just mentioning that. Like the example is that for a continuous valued attribute, you can have a Gaussian distribution. So if the values are occurring in the real domain, and then you know that in a Gaussian distribution, this is the probability distribution. So for a density function for a Gaussian distribution, and what you need to do for computing the probabilities or getting these distributions, you need to simply estimate these parameters. So that is what is parametric modeling. So given the data, now obtaining the likelihood for a particular class means within that class you estimate these parameters. One parameter is mu, another parameter is sigma, and I hope you understand their meaning in terms of Gaussian distributions. One is representing the expectation value or mean, the other one is representing the standard deviations, or that from the variances you can estimate that. So similarly, for every class, you have to compute its own parameter set for these likelihood functions. And once you get them, then the whole computations can be done for the Bayesian classifications. So a simple example is given here. It has been taken from a particular lecture slides, as you can see in the reference. So this example is simple. That's why I'm presenting them, but I will present in a quickly because it's not very difficult to understand. So you can see that actually there are certain training data set that is shown here in this table, and some of the variable names are not very clear because of the size, etc. So here actually what it is showing the a person's statistics, a subject's or a person's statistics, the person's age, income in categorical way terms, like whether the income is high, medium, or low, whether the person is a student or not, whether the person can take loan or not, or there are certain credit rating, certain categories, and finally, given that whether the person should be should be recommended for giving the loan for buying a computer, right? So this is a scenario. Suppose in a banking scenario, you are given this data, and your objective is that. So this is the data. So now, if I give you this is what you get. So as you say that class C1 buys computer, yes. Class C2 buys computer, no. Buys means in this case you are recommending for buying the computer. And suppose you have a data instance that a person having age less than equals 30, income is medium, person is a student, and the person's credit rating is fair. So in that case, whether you should recommend for for giving the loan to buy computer. That means the class, whether the person should belong to class C1 or class C2, right? So under the Bayesian framework, what you need to do, you need to compute the posterior probability of C1 given the given the instance X, and posterior probability of C2 given the instance X, and then you should choose that class, that means either C1 or C2, which is the maximum, whose posterior is maximum. Is it clear? So this is what you need to do. And for computing that, for computing this posterior, you can use this particular this particular training data, this particular training samples for computing this posterior. So that means I need to compute posterior. Given this data set, I need to find out posterior, that what should be the posterior probability of C1 given this thing. So which means if I use naive Bayesian classifier, I will find out what is the likelihood of a person being age of less equals 30 for class C1. Similarly, what is the likelihood of age less equals 30 for class C2, right? I need to do that for posterior each one. So what is the likelihood that income is medium for class C1, and what is the likelihood that the income is medium for class C2? And all these likelihood probabilities needed to be multiplied to get the likelihood of the whole data set, whole feature vector for class C1 as well as for class C2. So this is one way you can do it. You can do it numerically, right? You can find out the fraction of times a particular category is occurring. So these are all category here. As you can see, these are all category. Like age is also a category. It's not a numerical value here. Categories are, how many categories are there? For age, how many categories are there?
Three.
Sometimes I'm hearing very faint. Can you tell me once again?
The three.
Yeah. For age, it is 3. For income also, it is 3. For student, it is 2. For credit rating, it is 2.
It is 2.
Right? So these are the two, all are categorical data. So you just compute the fraction of times a particular category occurs given that class. Given that class. That means how many, if I consider all the observations related to yes, and within that observations, how many of them are in, say, less equals 30? What fraction of them is less equals 30? That would give me the likelihood of age is less equals 30 given the class C1, right? So in this way, you will be computing. And how do you compute the prior of class? How do you compute the prior of class? They are now, you observe this distribution. You observe this distribution and find out fraction of times the class C2 occurs and fraction of times class C1 occurs. This is the prior. Is it clear, this computation? So everything can be computed. So I'll go a bit quickly in this next slide. So you know that computation of class prior, you can see that this is the prior, right? So 9 times yes occurs out of 14. So these are the priors. Similarly, the likelihood estimation of age less equals 30. Now, those are shown in red, right? Those are shown in red color in the age occurrences are shown. So out of 14, you can see that there are 5 occurrences. Of course, out of 5 occurrences, some of them are of class no and some of them are yes. Now you have to individually find out, given that class, how many are occurring there. Yeah, it's okay. Since there are 9 occurrences of yes, so out of 9, only 2 are less equals 30. So likelihood would be 2 by 9. And similarly, likelihood for the class yes. Is it clear? You go for income medium also in the
Sir,
same
it's the end of the both instances, right?
It is the
And expression of both income and Bayes computer, right?
yeah. You find out. You find out that, yes, you should consider that, and then you also consider what is the total number of occurrences of years also, because what other values have occurred there. Now, so what fraction of time medium occurs when a person buys computer?
Yes, sir.
That is what. So fraction of time is 4 by 9. Is it clear?
Yes,
so that
sir,
is the
it's
line. Okay. So similarly for student and for credit rating also. So now you have all these likelihoods you have computed, and then like overall likelihood for a class Ci, you can see that I mean for two classes. So this is the overall likelihood. So if I use maximum likelihood based approach, which one to be chosen? Which class should be assigned?
Yes. Yes.
Yes. So that is a maximum likelihood based approach. But for Bayesian inference, we have to use maximum a posteriori probability based approach. So maximum posteriors basically. So estimation of posterior, as you can see that we have to also consider the priors, and then that is proportional. So this is the proportional value 0.028 for yes and 0.007 for no. So even for Bayesian inference also or map based approach also, the decision is the same in this case. So it is yes. But it does not give you the actual posterior probability. What should be the actual posterior probability? You have to divide it by the the data probability of X itself. Okay? So that combinations, how many times it. So you see that is not very trivial. Right. So there are one thing, some of the things that they are like, how do you avoid zero probability? Because it may occur in this kind of cases that no, one of the likelihood is zero, and that will basically make every values as zero. So it will ignore the all other likelihood computations. So we try to avoid that. So what we'll do, we usually give a very low probability for zero case, which means the counting may start with 1 only, even we don't consider 0. That means we take an additional count. For the number, we take an additional count. And in this way, we can compute this probability. We call it Laplacian correction, this one. So as you see that suppose a data set with 1000 tuples, income low is 0, other is 990, 10, but we add 1 for every category. So the total tuples, number of tuples is 1003. So by default, at least there is one occurrence, which means which are not in this data set. And in this way, you avoid zero. So what are the advantages and disadvantages of naive-based classifier? Just let us summarize. One, as you can see, it is easy to implement, and sometimes you can get very good results. In many cases, what it says. Now, but there are disadvantages, like you are assuming that these attributes are conditionally independent given a class. Now, which may not happen, which may not be there. This assumption may not be true. And then you will have your modeling will be inaccurate and you will get a lot of error because dependencies exist. For example, the different attributes like you consider in hospitals, patient's profile, age, family history, etc., symptoms, fever, cough, or disease, lung cancer, diabetes. So these attributes, they may not be independent, they may be related. So it cannot model the real world scenario. So this kind of dependencies among this cannot be modeled by naive-based classifier. So today, let me stop here. We'll continue these discussions and we'll see that what other kind of Bayesian inference mechanism is there. Even this kind of dependencies are also modeled in a convenient way to handle this situation. So with this, let me start. So is there any question? Okay, so in that case, we'll again meet. Yeah, please.
So we had doubts in the assignment part. So